our original equation yielded a fundamental set, of which one was this function, which has real and imaginary parts indicated here. Now I've used script R to stand for real part, and script I to stand for an imaginary part. So we can say that this matrix with the usual equation yields solution real plus I times imaginary, with the real part equal to this, the imaginary part equal to this. And I seem to be in the habit of not closing my parentheses. Okay, and these are both solutions to the original equation. So if I plug either of these solutions into my equation y prime equals ay, I'm going to get an identity verifying that each of these is a solution. Now, this raises the question. We've got two solutions here. Now let's return for a minute to the original solutions of the original equation. Remember that the original equation gave us these eigenpairs, this solution set, and this real and imaginary part here came from just this first solution function. We haven't even worked out the second function. And this is a solution set since we got this from distinct eigenvalues. But the question now is, could we get a simpler solution set just using the real and imaginary parts of that first solution function coming from the first set of eigenpairs without even considering the second? We can easily test whether we get a fundamental set. We just test the Wronskian equals the determinant of the fundamental matrix, or the determinant of our solution matrix, which is just the determinant of e to the 3t cosine 3t. I'm going to run into a little bit of a space problem here, so I'm going to spread this out a little bit, and e to the 3t sine 3t and 1/5 e to the 3t multiplied by 3 cosine of 3t plus sine of 3t. Okay, again, I got a little bunched up there. We need to test whether that determinant is not equal to 0. If it's not, then it follows that we do have a fundamental set. Now I'm going to rewrite this matrix so that we can really see it. Do that on a fresh sheet of paper off screen, and then we'll work out the determinant. First, let's close this set of parentheses. I managed to remember it here, but not here. Okay, I've simply rewritten the determinant, which is based on the real and imaginary functions, the proposed fundamental set Ri, script R, script I. We get this matrix, and we take its determinant. And the determinant is fairly easy to calculate. If we multiply this by this, or this by this, we're going to get an e to the 6t, and in fact we're going to get a 1/5 e to the 6t. So I'm going to factor out that 1/5 e to the 6t, and then multiply by what's left. We have cosine of 3t times 3 cosine 3t plus sine 3t. Get this down here so I don't write uphill too badly. We get 3 cosine squared of 3t plus cosine of 3t sine of 3t, and then from the other diagonal we get minus sine of 3t times distributed through this expression. So we get cosine of 3t sine of 3t plus 3 sine squared of 3t. And that equals 1/5 of e to the 6t multiplied by, we have 3 cosine squared and 3 sine squared 3t. So that just gives us 3. And the cosine 3t, sine 3t appears here as positive, here as negative. That's 0. So we simply get 3/5 e to the 6t, which is not equal to 0. So script r, script I forms a fundamental set. This means that any solution to the differential equation can be formed by a linear combination. I need a C1 here and a C2 here. Let me write that out just a little better. C1 times R plus C2 times I, and we don't need the imaginary number, the I there. Okay, we could have used C2 times I, the square root of -1 times R script I, because C1 and C2 can be real, complex, or imaginary constants. So just by adjusting C2, we could have an I in this form, square root of -1, little I, but it's totally unnecessary and redundant. Now, in our original equation, we've totally ignored our poor old second solution, e to the 3 minus 3it times the eigenvector 1, 1 minus 3i5. We haven't used it at all. We could have used it. We could have written it as a sum of a real and an imaginary part using the same manipulations, same sort of manipulations we used with this function. Okay, but we haven't done so. Still, this is a solution to the equation, so let's ask the question, can our solution e to the 3 minus 3it multiplied by the vector 1, 1 minus 3i over 5 be written in the above form? Since this is a solution, and since our general solution, put the arrow over the y, since our general solution is of this form, then it must be so. So can we solve C1R plus C2 script I equal e to the 3 minus 3it times 1, 1 minus 3i over 5 for C1 and C2. That's written kind of small, but you heard what I said. I'm not going to do that. I'm not going to take the time. Not going to fill up valuable disk space doing this. Wouldn't take class time to do this. I'll pose this as a problem, as a suggested problem. Prove that this solution can be put in this form where the R and I solutions are this column and this column of our psi matrix.